Hi, Algebra 2 students. Welcome back here. Today we are going to take a look at section 7.4. You should have your note-taking guide in front of you, and we're going to just work through this note-taking guide. We are going to talk about logarithms and the graphs of logarithmic functions. So what we need to do first is we need to kind of define what this logarithm is. So a logarithm is a way to rewrite an exponential function so that we can solve for x when x is in the exponent position here. So when we look at this exponential equation right here, b to the x power is equal to y, what we can do is we can rewrite that as a log, and the way we say that is log base b of y is equal to x. Okay, so every log is equal to an exponent. If you look at where the exponent is right there, x, a log is equal to an exponent. So what we're going to do here is look at the first three examples, and we're going to just practice rewriting these logarithmic equations. So if I have an example 1, let's look at that one. Log base 2 of 8 equals 3. I know the log's equal to 3, so that's the exponent. So it's going to be 2 to the third power is equal to 8. And 2 cubed is 8, so makes sense. In example number 2, we have log base 12 of 12 is equal to 1. So my base is 12, okay, that's that number, that's that 12, and the exponent is 1 because the log is equal to an exponent, and that is equal to 12. So 12 to the first power equals 12. And example 3 here, log base 1/4 of 4 equals -1. So -1 is our exponent, so 1/4 to the -1 is equal to 4. Okay, so that should make sense because if we distribute that exponent, we get 1 to the -1 over 4 to the -1, which means that we need to flip those guys around, and that way it equals 4. Okay, so now since we kind of know how to rewrite logarithmic functions as exponents, now we can evaluate logs, and we'll use our calculator if necessary, but I don't think we're going to need it for example 4 and 5. So if we look at example 4, what is log base 2 of 32? So this is equal to an exponent, right? So 2 to what power is equal to 32? And that means that 2 to the 5th power is 32, so that means that log is equal to 5. Okay, let's look at example 5 here. So what is log base 27 of 3? So a log is equal to an exponent, okay? So 27 to what power gives us positive 3? Okay, well, let's see here. I guess 27 to the 1/3 power is equal to 3 because that's the same as saying the cubic root of 27, and 3 to the 3rd power is 27. So that means that this log is equal to 1/3. Okay? All right, so we have what we call some special logs. We have two special logs, the common log that has base 10. Okay, so this is the log button that you see on your calculator. They're using base 10 there. So when you do not see a base, you need to assume that it's the common log which has base 10. And then we have what we call the natural log that uses base e. So log base e of x is what we call the natural log. We abbreviate that with ln for natural log. And if you see natural log and you don't see a base there, that means we're using the natural log base e. Okay, so what we're going to do here is I want you to take a moment and find your log button, that button you see on your calculator that says log, and I want you to find the button on your calculator that means natural log. And I want you to grab your calculator and I want you to plug in example 6. So you're going to simply hit that log button and hit 12. Okay? So what you should get when you evaluate log of 12, that's the common log base 10, you should get approximately 1.08. Okay? For example 7, you're going to use the natural log button. So you're going to press that natural log button and type in 0.75, and you should get approximately negative 0.29. Okay, so some of these we can evaluate them just with sort of mental math, and then some of them we need our calculator. Okay, at this point in time, we don't have a way to plug in any other base other than the common log base 10 and natural log base e. So if you have a log that has a base other than 10 or e, you need to rewrite it so that you can evaluate it with mental math. So we have a couple special rules here. So the inverse functions of logarithms, what we have is if we are looking at log base b of b to the x power, that's always equal to just x. And if we have b raised to the power of log base b of x, that's also equal to x. Okay? So let's look at example 8 here. If I have e raised to the natural log of 4, well, we know now that natural log uses base e. So you could essentially rewrite this as e to the natural log, natural log base e of 4. And then here, this is using this rule right here, okay? So what that means is if our base of our exponential function matches the base of our log, then that is equal to just 4. Example number 9, what we have here is we have log base 7 of 7 raised to the negative 3x. Okay, so our log has the same base here, so we're going to be using this rule. Okay, so that's equal to then just this exponent. So this is equal to negative 3x. Okay. Alrighty, so what we're going to do now is we are going to find some inverses. Okay, so we talked about inverses in chapter 6, and we're going to find some inverses of logarithmic or exponential functions. So we learned that when you find an inverse, the first thing you need to do is switch x and y. So what we'll do on example 10 is we will switch our x and our y. Okay? Now we solve for y. Okay? So y is in the exponent, and this is where our logarithm comes in handy because a log is equal to an exponent. So what we're going to do is we're going to use our rule. I'm going to write it up here. B to the x power equals y. So then that means that log base b of y is equal to x. So we're going to now rewrite, or excuse me, I should actually be going the other way. We're going to rewrite our exponential function as a logarithm. Okay? So then that means that y is equal to log base 4 of x. And just to kind of finish it off, let's change it to the proper inverse notation. So we'll write y inverse is equal to log base 4 of x. So that would be the inverse of y is equal to 4 to the x power. For example number 11, okay, we'll switch our x and y's. So x equals 1/2 raised to the y power minus 3. And the first step we should do is isolate our exponent. So let's add 3 to both sides. So x plus 3 equals 1/2 to the y power. And now we want to solve for our exponent. So we want to rewrite our exponential function as a logarithmic function. So what we have here then is, let's see, y equals, because that's our exponent, y equals log base 1/2 of x plus 3. Okay, it's really important that you put that whole quantity x plus 3 in parentheses. And the last thing we'll do is we'll just add our special little inverse notation there. So that is our inverse function. And number 12, we're going to find the inverse again here. So let's switch our x and y's. So x equals 5 log base 2 of y plus 1. Okay? So there's a couple different ways you can solve this problem. You could divide by 5. And there's another way we can solve it that we're going to learn in the coming sections once we learn a little bit more about logs. So let's go ahead and start by dividing both sides by 5. So x over 5 equals log base 2 of y plus 1. Okay? So this time, what we want to do is instead of rewriting our exponential function as a logarithmic function, we actually want to do the reverse, and we want to take our logarithmic function and rewrite it as an exponential function. So I'm going to rewrite this as 2 to the power of, I could say, 1/5 x is equal to y plus 1. Okay? So now we're getting close to solving for y. The last step would be to subtract 1 from each side. So y is equal to 2 to the 1/5 x minus 1. And let's just put our fancy little inverse notation there, and that is going to be our inverse. Okay? All right, so now what we're going to do is we're going to look at some graphs of logarithms. Okay? So the inverse is kind of a pretty important concept here, because graphing logarithmic functions can be kind of tricky. So if we know that y is equal to b to the x power, then its inverse function is y is equal to log base b of x. And we learned that inverses are going to be reflections over this line, y is equal to x. Okay? So since we've been practicing graphing exponential growth and decay problems, if we look at this function right here, which is an exponential growth function, okay, if we can graph that, say this is the point 0, 1, then we can flip that coordinate, and that will be on the inverse function, 1, 0. Okay? And if it's exponential growth, then its logarithm graph now is going to have a slightly different domain and range than you would see in an exponential growth function. So the domain and range are going to flip-flop each other. Okay, so the domain for the logarithmic function is going to be x is greater than 0. And that's because now we're going to have sort of this asymptote on the y-axis, and the function is going to be going to the right forever. So it's going to be all positive numbers. And then the range is going to be all real numbers. Okay? If we look at this other graph, if you see here, this is exponential decay. All right? So its logarithmic graph is going to look like this, okay? And that one is going to also have the same domain and range, all right? Now, if we look here at transforming logarithmic functions, if this is what we call our parent function, then this here is our translation. Okay, it looks very similar to a lot of the other transformations we've done in the past. So x minus h, that means that you're going to the right. It's the opposite of what you see in the parentheses. And then the plus k means we're shifting up. Okay, so if I look at this graph over here to the right, we have y equals log base 2 of x plus 3 plus 1. Okay, so how do we get that? Well, first we start off with we start with its parent function, y equals log base 2 of x. Okay, so here is that parent function. You can see it right here. There's the parent function right there. Okay, now when we look at our rules of transformations, when I see that plus 3, what that means is I'm really going left 3 units. So this graph tells us that the plus 3 means we're going left 3 units. And the plus 1 on the outside of the parentheses means we're going up 1 unit. Okay? So you can see on the graph that each point in the parent function is being shifted left 3 units and up 1 unit. Okay? So we start with this parent function, which is y equals 2 log base 2 of x, and then we just shift it accordingly. Now, when we shift graphs, sometimes that will change the domain and range. So for the parent function, we had this asymptote on the y-axis. And since we did a horizontal shift, that asymptote is now going to get shifted 3 units to the left. Okay? So now we have our function here going to the right of that line, which is going to change our domain to x is greater than -3. And the range is going to stay the same, so it's going to be all real numbers, so y belongs to the reals. Okay? So we're going to practice graphing a couple graphs here. Now, what I want you to keep in mind is the parent function and then also the inverse of that parent function. Okay, so we're going to do this in a couple steps. So if we're looking at the function y equals log base 2 of x minus 1 minus 2, the parent function is going to be y equals log base 2 of x. That's the parent function. Okay? And the inverse of that parent function, the inverse, is going to be, well, we could solve for it, but I'm going to just tell you what it is. We could switch our x and y's and solve for it. It is y is equal to 2 to the x power. Okay? So we know what that graph y equals 2 to the x power is. Okay? We know that it's going to start here at 0, 1, and then let's see, if I plug in a 1, that's going to give me 2. Okay, 2 to the first power. If I plug in a 2, 2 times 2 is 4. And then if I plug in a 3, 2 to the third power is 8. Okay, so we can kind of see this function here. This is the inverse function, right? So this is y equals 2 to the x power, all right? Now, to graph its parent function, okay, so to graph the parent function, what we do is we switch those x and y coordinates, okay? So instead of being at 0, 1, we're going to be at 1, 0. And instead of graphing 1, 2, we're going to graph 2, 1. And then we're going to graph 4, 2. And we're going to graph 8, 3. Okay? So you can see that parent function forming there. All right? So this is y equals log base 2 of x. All right? So then the final step now is we are going to translate that logarithmic function using our rules of translation. So what this means is if we look at our function here, the translation, which is y equals log base 2 of x minus 1 minus 2, that means that we are going to shift right 1 unit, and we're going to shift down 2 units. Okay? Remember, it's always the opposite of what you see in those parentheses is the horizontal shifting. So we're going to take our parent function and we're going to take each point and we're going to shift it right 1 and down 2 units. Okay? Right 1, down 2 units. All right, so now the graph is going to come up through here and go to the right. So this is going to be y equals log base 2 of x minus 1 minus 2. All right, and so lastly here, we're going to state our domain and range. So the domain of the function, you can think about, since we did a horizontal shift to the right, now we've shifted our asymptote on the graph 1 unit to the right. So our domain is x is greater than positive 1. So we're just always on the positive side of that asymptote 1. And for the range, it's just going to be y belongs to the reals. Okay? Now for number 14, let's try this one. What we're going to do is we're going to first start by writing our parent function. Okay? So the parent function of the graph is going to be just y equals log base 3 of x. That's the parent function. Now the inverse function is going to be y is equal to 3 to the x power. Okay, so we're going to graph that inverse function to start us off here. And so 3 to the x power, let's see, when I plug in 0, I get 1. 3 to the first power is 3. 3 to the second power is 9. Okay, so this is the inverse function here. That is y is equal to 3 to the x power. Now to graph our parent function now, so to graph this function, we are going to now switch our x and y's. Okay, so we're going to be at 1, 0, 3, 1, and 9, 2. So this here is our parent function. That's our parent function. Okay. Now, what we want to do next is look at the translation of that. Okay. So how are we going to translate y equals log base 3 of x to y equals log base 3 of the quantity x plus 4 minus 3? So for the translation, we are going to take the function log base 3 of x, and we are going to shift the graph left 4 units, and we're going to go down 3 units. Okay, so from that red graph, we're going to shift everything left 4 and down 3. Okay, so our graph is going to come up through here and travel to the right. Okay, so that's going to be the translation. Y equals log base 3 of x plus 4 minus 3. Okay, so for the domain and range, since we shifted the graph left 4 units, what happens is the asymptote on the y-axis also gets shifted left 4 units. Okay, so that means then now our domain is everything to the right of that asymptote. So x is greater than negative 4. And for the range, again, y belongs to the reals. Okay? All right, so you're going to find your homework, and you're going to be working on section 7.4 for the next couple days. And remember, if you have any questions, make sure that you go and visit the Math Tutorial Lab in F107. There's some really nice teachers that are more than happy to help you answer your questions. Happy graphing, and we will see you next time.